2.6 are notes on stoichiometry, mole to mole, in the unit Foundations in Chemistry Part 2. We are looking at the outcome FC3, using stoichiometry to determine the relative amounts of substances consumed and produced in chemical reactions. Lovely. Even there, brace yourself, stoichiometry is coming. Because the next 6 sections are based off of stoichiometry. Just building on what we learned in 2.1, 2.5, but taking it a step further. We will learn how to determine the relative number of moles in a variety of chemical reactions using balanced chemical equations, how to relate the use of a mole to coefficients in a balanced chemical equation, and how to perform stoichiometric calculations to predict the outcomes of chemical reactions using the correct units and significant digits. What the heck does it mean? Derived from two Greek words, stoichion, which means element, and metron, meaning measure. Basically, it means mathematical calculations of quantities in a chemical reaction. So our little disclaimer here that the rest of this unit essentially combines all of the information we've learned up to this point. You need to be able to name and give formulas for chemical compounds, create chemical equations, balance chemical equations, and use mole calculations. If you struggled with any of these concepts, take the time to go back and review them. Also, make sure to stay on top of your homework and come at lunch for help if you need. Well, mole ratios will be used in every stoichiometry question, so it's important we understand how they work, and mole ratios are derived from coefficients of chemical equations. So if we keep following along with these examples, we'll figure it all out. For example, 2 hydrogens plus oxygen yields 2 waters. We have a ratio of hydrogen to oxygen, which is 2 to 1, or 2 over 1. We have 2 hydrogens to 1 oxygen, which means for every 2 moles of hydrogen, there's 1 mole of oxygen. And the ratio of hydrogen to water is 2 to 2, or 2 over 2, or 1 over 1. For every 2 moles of hydrogen, there's 2 moles of water. So there, we're starting to see we can find some little conversion factors. It can also be inverted depending on what we're comparing, or we can go from oxygen to hydrogen, which our ratio for that would be 1 to 2, or 1 over 2. For every 1 mole of oxygen, there are 2 moles of hydrogen, and a ratio of water to hydrogen, which is 2 to 2, or 2 over 2, or 1 over 1. For every 2 moles of water, there are 2 moles of hydrogen. So, 5 steps for solving any of these stoichiometry questions. We need to make sure we write a balanced chemical equation, identify known and unknown variables, take whatever value is given in the question and convert it to moles, use the mole ratios from the balanced chemical equation to rebalance the equation using the mole value you calculated, and go where the question's asked using the rebalanced equation. What do these questions look like? If we consider our reaction there, 4 ammonia plus 5 oxygens yields water plus nitrogen monoxide. It says how many moles of water are produced if 0.176 moles of oxygen are used. So our first step is writing a balanced chemical equation, and then we identify the known and the unknown. So we have a balanced chemical equation. Sometimes I find it best to write them out again. So if I write out my balanced chemical equation again, we have 4 ammonias plus 5 O2 yields 6 H2O plus 4 nitrogen monoxide. And then, to figure out what I know and I don't know, I write that underneath whatever compound that corresponds to in my chemical equation. That's why I rewrite it. So it says how many moles of water, so I'm looking for moles of water, I'd write question mark moles, are produced if we have 0.176 moles of oxygen. So 0.176 moles of oxygen. Write that under oxygen. Now I've written what I know and don't know, and then I take whatever's given in the question and convert it to moles, which we were given 0.176 moles. It's already converted to moles. We can skip that one. Oops, wrong way. And it says use the molar ratios from the balanced chemical equation to rebalance the equation based on the mole value. So now we need to use our molar ratios. Oh, we have 0.76 moles of oxygen that was given to us. It's already converted to moles. We don't need to convert it to moles. Then it says use our molar ratio. And our molar ratio, we look to our coefficients, those numbers in front of our chemical compounds. Well, there's 5 moles of oxygen, and if we look, we have 5 moles of oxygen on the top, so we need to we have moles of oxygen on the top, so we need to put 5 moles of oxygen on the bottom, and we have 6 moles of water that we put on the top. Now we put 6 moles of water on the top because that's what we're looking for. If we were looking for moles of nitrogen monoxide, you put 4 moles of nitrogen monoxide on the top. If we were looking for ammonia, we would put that on the top. Whatever you're looking for, you need to put that on the top. Because our moles of oxygen now cancel out, and we're left with moles of water. So that lovely conversion factor, that's our molar ratio, using those coefficients in our chemical reaction. So if we work that out on our calculators, 1.76 times 6 divided by 5, we get 0.2112 moles of water, but we need to write that to proper significant figures, so we have 0.21 moles. 211 moles of water is our final answer. And then our second question, how many moles of nitrogen monoxide are produced in the reaction if 17 moles of water are also produced? So again, our first step, we need to write that balanced chemical reaction. And like I said, it's helpful to rewrite that reaction out every question. We have 4 ammonias plus 5 oxygens yields 6 waters plus 4 nitrogen monoxide. We need to write our knowns and our unknowns next. We have 17 moles of water, so we write that 17 moles under our water, and we're looking for moles of nitrogen monoxide. Then we start with what's given to us in our question and convert to moles, which it's already converted to moles. So we will then go to the next step, which is using the molar ratio. And just as a side note, since I don't think I've mentioned it yet, it's really important to write, this is 17 moles of water, because we need to figure out what's on top, so we use our molar ratio to figure out where the coefficient goes. So now we know, we have moles of water on top, we need to write the 6 moles of water from our coefficient on the bottom, so those two things cancel out. And then we write 4 moles of nitrogen monoxide on the top because that's what we want. So we want to be left with. And then if we work that out on a calculator, 17 times 4 divided by 6, we get 11.333. Repeating, which it looks like we have to two significant figures. 11 moles of nitrogen monoxide. Another example here. How many moles of aluminum will be needed to react with 12 moles of copper 2 chloride solution? This one's a little bit tougher. We're not given our chemical equation, which is why it's important we know how to do this from last unit. This is how many moles of aluminum will be needed to react with copper 2 chloride solution. We have aluminum plus copper 2 chloride, which CuCl2 yields, and if we take a look, this is a single replacement reaction, so we got A, B, C, A, C, B. We get copper coming out by itself, and we have aluminum chloride going together. And I'm going to erase the A, B, C's just so I can write my knowns and unknowns underneath. Continuing on with this, we need to balance our chemical equation. So most notably, I see that we have 2 chlorines on one side and 3 chlorines on the other side. We need to make sure those are equal. We had a 2 in front of aluminum chloride and a 3 in front of copper 2 chloride. And then we need 2 aluminums and we need 3 coppers. That should be balanced and good to go. And then we write our knowns and our unknowns. How many moles of aluminum? We question mark moles. React with 12 moles of copper 2 chloride solution. Now that we've written our knowns and unknowns, we start with the number that's given to us in the question, 12 moles of copper 2 chloride, and we convert to moles. It's already converted to moles, so then we can use our molar ratio, which is those coefficients in front. We have moles of copper 2 chloride on top, so we need to put moles of copper 2 chloride on the bottom, and we use 3 from our coefficient, and then we're looking for moles of aluminum. We use our coefficient of 2 that goes on top. Our moles of copper 2 chloride cancel out, and we're left with moles of aluminum. We go 12 times 2 divided by 3, and we get 8. Looks like 3 significant figures here. 8.00 moles of aluminum is our final answer. And another example here. How many moles of oxygen gas are needed to react completely with 3.5 moles of hydrogen gas to produce water vapor? Oxygen gas plus hydrogen gas forms water vapor. And we have to balance this, so we need a 2 in front and a 2 in front there, and it's balanced. Balanced chemical equation number 1 is done. Then we write our knowns and our unknowns. Ask how many moles of oxygen gas are needed to react completely with 3.5 moles of hydrogen gas. We have our knowns and unknowns. We start with our number in the question and convert to moles. It's already converted to moles, so we're good to go. We need to then use our molar ratio as our next step, which are coefficients. We have 2 moles of hydrogen on the bottom to cancel off, and 1 mole of oxygen on top, because that's what we're looking for. And then we type that into our calculator. So 3.5 times 1 divided by 2, we get 1.75 moles of oxygen to the proper significant figures. And our last question here, how many moles of ammonia gas can be produced, that's a product, by reacting hydrogen with sufficient nitrogen. And we have hydrogen gas plus nitrogen gas. And ammonia isn't on anywhere on your periodic table or anything. It's a compound that's just really, really common. It has its common name, ammonia, NH3. If you'd like to write that down somewhere, that's completely fine, just because it shows up quite a bit and just don't want to get confused. So we have, to balance our chemical equation, we'll need a 2 in front of our nitrogen and then a 3 in front of our hydrogen. And then we write our knowns and our unknowns. So our knowns, we have 6 moles of hydrogen gas. And it's looking for how many moles of ammonia gas are produced. And then we start with our number given to us in our question. We convert it to moles. It's already converted to moles. So we use our molar ratio, which are coefficients from the question. So we have 3 moles of hydrogen on the bottom, so it cancels off. And 2 moles of ammonia on the top. So we're left with moles of ammonia, and then we plug that into our calculator. 6 times 2 divided by 3. We get 4. Looks like to 3 significant figures, 4.00 moles of ammonia. Remembering we only look for our significant figures from the numbers in our question. And there we go. There's mole to mole stoichiometry. Not so scary.